Well, hello again. In this example, you will learn how to calculate reactions when dealing with inclined loads. We're going to look at this basic frame. It has a distributed load on member AB, point load out at point D. We are being asked to calculate the reactions that result from these applied loads. So first thing is to identify where the reactions are possible. So at point A, we have a pin support, which means two orthogonal reactions will occur. Point C, we have a rocker, which only produces a reaction that is orthogonal to the support surface. Before we actually calculate any numbers, let's double check our determinacy on this. The total number of unknown forces here is 3. We didn't make any cuts, so we have only one structural piece, which means that the total number of equations of equilibrium which we have are 3, and so of course 3 is equal to 3, which then means that we are statically determinate. And our reactions are not all parallel and they are not all concurrent, so we can also conclude that we are stable here. So let's go ahead and sketch a free body diagram of this. I'm going to go ahead and start labeling these. So this vertical reaction is the reaction at CY, RAY, and RAX. Looking at the dimensions of all this, you'll notice that this is 45 degrees. Okay, so dealing with the 30 kip point load, that's easy enough, but that distributed load, we need to turn that into an equivalent point load. We will do that by taking the intensity, that's 3 kips per foot, and multiplying it by the length over which it is acting, which is 14.14 feet, and that will be equal to 42.42 kips. So here is our resultant, 42.42 kips, and that dimension will be, of course, half of that distance, 7.07. Or if you wanted to look at the vertical projection of that, it would be 5 feet down. Now, if we're going to run any kinds of equilibrium equations on this, it may be convenient for us to convert these into vertical and horizontal components, and so that's what we're going to do. Convert that into components. So I'll say the force in the x will be force times the cosine 45 degrees, and that'll be 30 kips. Force in the y will be whatever that force was times the sine of 45 degrees, and that's also 30 kips. So we'll go ahead and put it up there like that. But before I move on to running the equations of equilibrium, I want to point something out very quickly, and this is something that can be very convenient for you as you move on. Whenever you have an inclined distributed load like this, if you were to actually look at the intensity, which is 3 kips per linear foot, and if I want to know the vertical component of that, I can simply use that projected distance right there. And so, as you'll notice, you get 3 kips per foot, and multiplied by 10 feet, and that will be 30 kips. So I could have actually gotten directly to that quantity. And in a like fashion, I can get the horizontal component by looking at that vertical projection right there, which is 10 feet. So 3 times 10 will be 30, and so we can confirm that. That's just an alternate way to do those calculations. Doesn't have to be restricted to something that's 45 degrees. Just really, anytime you have horizontal and vertical dimensions, you can take that little shortcut to get your answers. Okay, once we've got the free body diagram sketched, we are ready to use equilibrium. So the first thing I'm going to do is solve for the reaction CY, and I'm going to do that by summing moments about point A. And so I've given a little sign convention here where I said counterclockwise I will consider to be positive. So I'll deal with the point load first, 30 kips by 5 feet plus a negative 30 kips multiplied by 5 feet minus 30 kips multiplied by 22 feet. And all of that is going to be equal to 0 once we add in the reaction multiplied by its moment arm, which is 16 feet. Okay, let's look back at the free body diagram very quickly. If we are summing moments, you'll notice here that this 30 kips causes a clockwise rotation, this 30 kips causes a clockwise, and this causes a clockwise. And that's why those are all the same sign. The negative, negative, and negative. So I can go ahead and compute that out. RCY will then be equal to a positive 60 kips. It comes out positive, meaning I assumed the correct direction. Since I assumed upward, then I know that that reaction is indeed upward. Next equilibrium equation I'm going to use is I will sum forces in the y direction. And I'm just saying that the positive direction I'm considering is up. So my unknown, I have RAY minus 30 kips plus RCY minus 30 kips. All that is equal to 0. We already know RCY was 60 kips. And so if you do this, RAY computes out to actually be 0. That was an unexpected response. It just so happens that all the loads are perfectly balanced, so that is the case, that RAY does indeed work out to be 0. We are confident in that because we have followed the rules of statics when we have done the calculation. Now we've got one more to do, and that is we need to sum forces in the x direction. So RAX plus 30 kips is equal to 0. So RAX is equal to negative 30 kips. And because it came out to be negative, I know that it's not in the direction that I assumed. I had assumed it was acting to the right. The negative tells me that it actually acts to the left. So that is an interpretation error right there, telling me what the negative actually means. Well, that concludes this example. As always, it's an absolutely beautiful day to study structures.